Hello, mathematicians. Today we're looking at the normal distribution. It is considered arguably the most important distribution in statistics. Many of the measured quantities, especially continuous data, uses the normal distribution. So some examples of things that are normally distributed include height, masses, ages, random errors, and examination results. So let's look at the properties of the normal distribution. The first one is that it is a bell-shaped curve. The next property is that it is always symmetrical about mu, or the mean of the data set. Next, we know that its variability is measured by the standard deviation. So the symbol that you see on the screen here is sigma. And then lastly, the area under the curve is equal to 1, and the area under the curve represents the probability. So here is the bell-shaped curve of the normal distribution. Right at the center is our mean, and then to the left and to the right, we can have one standard deviation above the mean, one standard deviation below the mean, and the area between those two dotted lines there represents a probability. So what's the likelihood that a certain random variable falls between those two numbers? Okay, and classically, we look at something called the empirical rule. So if data falls between one standard deviation of the mean, it usually has a 68% likelihood of occurring. The notation that we use to represent normal distribution is as follows. So X, capital X, represents our random variable, and we use the tilde symbol to say it's distributed a certain way. So in this case, we say that X is distributed normally, so capital N, and we used the mean as well as the variance to represent our normal distribution. Okay, so here we see sigma squared. So sigma squared is the variance, although most of the time we will see the value for the normal distribution represented as a standard deviation. Okay, so when we were looking at discrete random variables, like the binomial distribution, we know that lowercase x can only take on integer values. But for continuous random variable, capital X, lowercase x can take on any real value. Probabilities, again, are found by finding the area under the curve of the probability distribution. So for example, in this diagram that you see here, that shaded region is the probability of a value falling between C and D. Here's the empirical rule that I referenced from that first slide. So for normal distributions, we use the 68, 95, and 99.7% rule. What that means is that in a normally distributed data set, 68% of the observations are going to fall within one standard deviation of the mean. 95% of the data will fall between two standard deviations of the mean, and finally 99.7% of all the data or observations will fall within 3 standard deviations of the mean. That means it's a really extreme case. So if something falls more than 3 standard deviations from the mean, it is not considered quote unquote normal. Okay, the 68, 95, and 99.7% rule is the empirical rule. You will not be required, or you will not have access to a calculator when using this property or this rule. So those are quantities that you have to memorize. This is not in your IB formula booklet. Okay, so let's look at the first example. Proud is a very good long jumper. The distribution of the length of her jumps follows a normal distribution with a mean of 6.4 meters and a standard deviation of 0.21 meters. Use the empirical rule to help you answer the questions that follow. Pause the video now and try this question on your own first. Okay, assuming you've taken some time to try this question, let's look at the solutions. A, what percentage of Proud's jumps will be between 6.19 meters and 6.61 meters? Okay, this is a no GDC question. So first, let's define our random variable x to be the length of Proud's jumps. And we know that x is distributed normally with a mean of 6.4 and a standard deviation of 0.21 or a variance of 0.21 squared. We always write down the normal distribution as the mean and the variance, even though we mostly use the standard deviation, okay? So that's just how the notation works. Okay, so let's sketch out this scenario. We know that the mean is 6.4, and we know that if I subtract one standard deviation from the mean, I'm going to get 6.19 because a standard deviation is 0.21. So 6.4 minus 0.21 is 6.19. One standard deviation above the mean gives us 6.61. So that first question shows us that I'm looking for a probability that's within one standard deviation of the mean. By the empirical rule, I know that that probability must be equal to 68%. Please pay attention to the correct notation that we use to illustrate this. Let's look at example B now. What percentage of Proud's jumps will be between 6.19 and 6.82? Again, let's sketch a useful diagram. We'll start with the mean. We already know that 6.19 is one standard deviation below the mean. Now, the value of 6.82 is going to be two standard deviations above the mean. So what is that probability going to be? Well, in order to figure out the probability to the left of the mean, I know that the empirical rule tells me within one standard deviation of the mean, that probability is going to be 68%. So divide that by 2 to get 34. Now, how many observations fall within two standard deviations of the mean? That's 95%. So if I look at that area to the right of the mean, I take 95%, divide by 2. When I add those two probabilities up, I get the left side of the mean, the right side of the mean, and that equals 81.5%. And finally, for C, what percentage of Proud's jumps will be less than 5.98 meters? So again, sketch the curve. Here's the mean. And then two standard deviations below the mean gets me 5.98. And I want to know the percentage that is below 5.98. So imagine me shading this region right here. What does that represent? Okay, so let's think about this. I know that 95% of the values fall within two standard deviations of the mean. So what's left over? What's left over is going to be 5%, but this is 1/2 of the curve, so I have to take that and divide by 2. So 2.5%.